Hello, my name is Olivia Paradis, and I am a rising senior at Rensselaer Polytechnic Institute, dual majoring in biomedical and electrical engineering. As a member of the SURF program cohort for 2018, shown here, I got the chance to pursue research at the University of Florida this summer. Today, I am here to tell you about my research experience with the Interdisciplinary Microsystems Group for the Electrical and Computer Engineering Department in the Herbert Wertheim College of Engineering. My research was guided by my mentors. Shown left is Kartik Santi, an electrical engineering PhD student that helped me every step of the way. Second from the left is Dr. Nishida, my faculty mentor in the Electrical and Computer Engineering Department, and on the right is Dr. Fan, my faculty mentor in the Mechanical and Aerospace Engineering, Biomedical Engineering, and Chemistry Department. I primarily worked in Dr. Fan's lab. Shown are several of the current members. His lab specializes in microfluidics and biomedical microelectrical mechanical systems, or BioMEMS for short. I worked on the microfluidic device fabrication and characterization project. To learn the basics of microfluidic device fabrication, I fabricated simple impedance-based cell counters. Cell counting has numerous applications such as blood cell counts for point-of-care diagnostics, determining cell behavior in response to infections or drugs, and determining cell concentrations for experiments. I used polydimethylsiloxane, or PDMS, to form the microfluidic channels and screen-printed silver to form the probes. In essence, the microfluidic channels are meant to focus the stream of cells such that cells pass through the probes one by one. Since a cell is less conductive than the surrounding media, the path length of the electricity between the two probes is increased when a cell passes through. In other words, electricity prefers to go around the cell. This alters the impedance between the two probes. An impedance analyzer is used to detect this impedance change over time. This data is used to count the cells. After the devices were fabricated, I tested them to characterize their performance. First, I did static tests, or tests with solutions simply sitting inside the device. The purpose of the static test is to gather impedance data over different frequencies to characterize the sensitivity of the device to different relative permittivities. Shown is my impedance data over different frequencies for air, 20% PEG solution, and distilled water. The impedance data is the sink between the three cases, which is ideal. This means the device is indeed sensitive to different relative permittivities. I then conducted dynamic tests, or tests with actively flowing solutions with a syringe pump in my case. The purpose of the dynamic test is to gather impedance data over time at one frequency, which is how cells are counted using impedances. To simulate a cell solution as best I could with available materials, I prepared a solution with microbeads. Shown is my impedance data over time for the microbead solution and distilled water for comparison. The distilled water impedance is fairly regular, but the microbead solution impedance has several spikes. This is due to the microbeads passing through the probes. This means the device is indeed able to detect the microbeads. There were several improvements that could be made, such as improving the way the probes are fabricated using 2 pairs of probes instead of 1, smaller channel sizes, and implementing hydrodynamic focusing, etc., etc. But one thing is for certain, these devices are an excellent start to developing new improved devices that could potentially be used to detect viruses, characterize cell membranes, and possibly provide insight into the inside of the cell at higher frequencies. In conclusion, I learned how to make microfluidic devices, how to conduct a literature review, and to really stop and think about how everything is working or not working, and always look for potential improvements. Overall, I look forward to applying to a PhD program at the University of Florida in the Electrical and Computer Engineering Department. Wherever I go, I hope to continue research in the bioinstrumentation field. I would like to say a special thank you to University of Florida for funding the SURF program, and for Provost Mike Nazareth and Julissa Nunez, as well as all the faculty mentors and everyone at the Fan Lab, especially Kartik. Thank you for watching.